Good afternoon, everyone. Welcome to our WIMBA call on Chapter 12. And so, unless there's any questions before we get started, I would like to jump right into the material. Okay, so just let's take a check-in on our course framework and see where we are. As I stated in an earlier WIMBA session, the framework for this course is built on how decisions are made and how planning is done in a typical business. So we said that in terms of planning and controlling a lot of the operations, we start with a forecast, and then we go into aggregate planning. And aggregate planning is a way to make sure you have the best and the best type of capacity available for the demand forecast that you have. After you decide on an aggregate plan, and because again you're looking at aggregate types of products or services, then the master schedule breaks that aggregated demand down to end item level. So for example, if you were forecasting 6 different cell phone models, once you do the aggregate planning step, then you break it down into Model 1, Model 2, Model 3. So at the master schedule level, you have end item demand. It's no longer aggregated. All right, so now we're at the point where we have to look at each item, and then we have to decide how much inventory do we need to store at the end item level. Now again, keep in mind, the more inventory we have, the higher service level we'll have. And I'm going to define service level as the probability that we will fill an order. Unfortunately, the higher our customer service level is, the higher our inventory carrying costs are. So there's a trade-off there at this point, and we have to decide what is the best way to make that trade-off. And so that's what Chapter 12 is all about. All right, so if you read Chapter 12, it talks a lot about what types of purposes does inventory serve. First and foremost, we carry inventory to meet forecasted demand. And so again, the reason we have that forecast is it's going to tell us, to some degree of accuracy anyway, how much in terms of products or services we should expect in the coming month. The second one, to smooth out process requirements. You may have different steps in the process that work at different speeds. And so, again, you might want to, if you have one process that runs half as fast as another, you might want to have some inventory to kind of balance out the faster one from the slower one, just so that you don't starve a downstream process that might run faster. To decouple operations would mean, again, it's just kind of like you can either decouple them through different parts of a system, or they can even be right next to each other, but again, it just allows one step to run while the other step, again, may not be either running or within the same geographic area. Stockouts, again, are just when we don't have inventory. So keep in mind that when we make a forecast, there is still going to be some error. And so let's say that our forecast is 100 units and we have an accuracy of 5%. All right, so if we make 100, there's a 5% chance, or there's going to be maybe 5 units more. If we have, for instance, a forecast accuracy of 5%, that means it can be as high as 105, could be as low as 95. And so if we only make 100, then there's still a chance that we've overproduced by 5 or underproduced by 5. And so what we do to protect ourselves against that error that we're going to have in our forecast is we carry inventory. Order cycles would be an example of, we might, for instance, if we buy a product or service, at like every month we do a resupply or something like that, we may just trigger a reorder independent of what we have, just to take advantage of some efficiencies in the ordering process. And then we can do the same thing with price, and we're going to look at quantity discounts where we can buy more at a lower price and still save money. Okay, so again, if we expect the price to go up, we might want to buy inventory at a lower or at the current price to save money, or again, just to take advantage of, if we buy more, we might be able to get it at a lower price per unit. Okay, so we've talked a little bit about costs. Well, what are the costs? The first type of cost is the holding cost, or sometimes it'll be called CC, carrying cost. And these are any costs associated with storing the items. And from an accounting perspective, this includes taxes, depreciation, warehousing, and it also can be opportunity costs, because again, if you have your money tied up in inventory, you're not able to invest it. So there's an opportunity cost for having your money tied up in inventory. The rate at which we hold inventory is called H, and H is in the units of dollars per unit per time. The ordering cost is another cost, and this is any cost associated with ordering and receiving the inventory. So in a big company, if you have a receiving department, or if you have a purchasing department, these would be all the direct and indirect costs associated with those departments, as well as with the product or service that you're ordering. Now, the order rate is called S, big S, and it's in the units of dollars per order. The shortage cost would be any cost associated with either not having the product at all, which is a stock out, or not being able to deliver it in the period that it's ordered, which is a backlog. And so anytime you have situations like that, either the customer waits or they don't get it at all, you're going to potentially have a lost sale, loss of goodwill, late charges, expediting, a whole bunch of things, again, to compensate for that lower service level. And then finally, you have purchase costs, is just the cost to purchase the inventory. And so this is just the price per unit times how much you buy, which is the demand. So in Chapter 12, we're going to look at two general types of models. The first one is how much to order, and we'll look at the basic EOQ and the quantity discount functions, and then when to reorder, the reorder point models. There are, again, like 4 or 5 of those, and we'll look at each of those as well. Okay, so in terms of understanding just some of the terminology that we're going to be using, the EOQ, it stands for economic order quantity. And so if you look at like how inventory relates, you order, let's say you order milk for the house. Let's say you order your 2 gallons of milk per week. And then over the course of the week, the milk is used, right? So the amount of inventory that you have of milk is going to drop, obviously. And so when it gets too close to zero, oh, it's time to go shopping again, get my 2 more gallons of milk, and again, the cycle continues. So this is what's called a sawtooth diagram. Now, it represents how an order quantity dissipates over time. So the slope of this diagonal line is the demand, all right? So what we're going to do is use the sawtooth diagram to look at how inventory changes over time. Now, the basic assumptions with the EOQ is we're dealing with one product. Demand is known and constant, so is lead time. I'm receiving orders in a single delivery. So again, we're not doing any quantity discount. We don't have any safety stock, you know, that kind of thing. It's a very simplistic type of model. Okay, so let's take a look at our same example here. Let's say the demand for milk is, let's say I need 10 gallons a week. So if I buy, let's just call this 1 gallon down here. All right. So if I buy 1 gallon, and then at the other end I could buy 10 gallons. Okay. So if I buy 1 gallon a week, that means I'm going to have very low holding costs because my holding costs are just going to be, a gallon at a time. Versus if I go and order all week, 1 week's worth, I have to go get 10 gallons. So I need a bigger refrigerator to hold 10 gallons. So if we would model our holding costs are going to be really low when our order size is low, and they're going to be really high when our order size is high. All right? So this straight line here, this is holding cost, and this is going to be equal to 2 over 2, which is the average inventory, and then we're going to multiply it by the holding rate. So that's our holding cost. If we take the same example here, again, if we buy 1 gallon versus 10 gallons, let's say the ordering cost then is I have to make 10 trips to the store. Okay, so that's a lot of trips. Versus if I buy only if I buy 10 gallons, then I just have 1 trip to the store. So if we look at how the amount of ordering varies over the quantity, we can see that it starts really high with low order sizes and ends up low with big order sizes. All right. So this kind of exponential looking curve is the order cost. So I got running into my phone line here. So this is going to be D over Q times S. All right? And that's supposed to be a big S. Sorry about that. And so if I look at, so then this is my holding cost and my ordering cost. And so if I look at total cost, that's this line up here. All right? And you can see that there is a minimum here in my total cost curve. Okay? And again, the total cost would just be the sum of the ordering cost plus the holding cost, right? So you can see the minimum total cost is going to be where the ordering cost intersects with the holding cost. And this quantity where that intersection occurs is called the EOQ, all right? So the EOQ is the quantity that minimizes the sum of the ordering and the holding cost. Okay? And so by definition, the EOQ is going to be equal to the square root of 2 times D times F over H. So that is how you can calculate this economic order quantity that, again, is going to give you the best quantity that's going to minimize the sum of the ordering plus the holding cost. Okay, so here we are. So I just kind of talked a little bit about, this is the EOQ formula, where D is the demand, F is the order cost or ordering rate, and H is the holding rate. The other formula that you will need is the total cost formula, which is, again, just the ordering cost plus the holding cost. All right, so as an example, if you look at problem 12.5, it gives us that demand is $19,500 a year. The ordering rate is $25 an order, and the holding rate is $4 per unit per year. So they ask, again, what is the economic order quantity? And so again, if you calculate that out, you get 494 workbooks. And then it wanted to know what the annual holding costs were and what the annual ordering costs were. All right, so again, I've shown you how to apply each of those with the information given. Now, one thing I will caution you about is that demand has a time unit on it, as well as the inventory holding costs have a time unit on it. These time units have to balance or be equal to each other in order to use this EOQ formula. So for instance, you could not use demand per month and holding rate per year. You're either going to have to convert the demand to annual demand or the holding rate to monthly. So again, just make sure those time units cancel out, and you should be able to, again, directly employ these formulas to calculate your total cost as well as your EOQ. Okay, so the next, so how much to order is the EOQ formula. It tells you, again, what your quantity should be that minimizes your total holding plus ordering costs. Now, one of the assumptions of the EOQ formula is that price is constant. So what we're going to do is we're going to break that assumption, and we're going to no longer require that price is held constant. So that's what quantity discounts are. So again, for anybody who's gone to what am I thinking of? I just went brain dead. It's where you can go, you can go and buy more than what you need. And for some reason, I just went brain dead on the store. But again, you can buy things in bigger quantities than what you need. And so the benefit there is they sell it at a lower price per unit. But again, you have to, so for instance, if you need a bar of soap, you're not going to be able to buy a bar of soap at these big discount places. You have to buy like a pack of, 24 or 30 bars, whatever, to get it at that lower price. All right, so how we're going to handle quantity discounts. It's a 3-step procedure. We're going to start at the lowest price and calculate the EOQ. If this EOQ is feasible at the price we calculated it at, then we are done. We don't have to do any more analysis. Then this EOQ is our lowest cost quantity to order. If that quantity is not feasible at the lowest price, you have to keep going up in price until you find a feasible EOQ. All right? And then the last step is to calculate the total cost for the feasible EOQ quantity and all other lower price break quantities, and then select the lowest total cost. So that sounds really complicated, but I have an example here that I think will show you these 3 steps. Okay, so, and I'm gonna get my Excel sheet opened up here so I can calculate these as we're doing them. In this particular problem, this is problem number 23. It gives us that demand is 20,000 per year, and that the holding rate is 20% of price, and that the ordering rate is $40 per unit. All right, so the first thing you're going to do is you're going to figure out what H is. All right, the holding rate, it says it's 20% of cost. So the holding rate for the highest price is $4, and then it's $3.60 for the middle one, and then it would be $3.40 for the lowest price. So you can see the lowest price is $17, and H is 20% of that price. So 20% of $17 is $3.40. Okay? So now, number 1 says we start at the lowest price. And so we're going to calculate the EOQ, which is just the square root of 2 times the 20,000 times the 40 divided by $3.40, and you get 686 is your EOQ quantity. All right. Now, here's where you ask, can I buy 686 units for $17? Well, the answer is no. You have to buy over 1,000 units to get this $17 price. And so this is not feasible. This EOQ, I cannot buy 686 for $17. So I'm going to put not feasible there. All right. So what it says, the process says, I have to keep going up in price until I find a feasible EOQ. All right, so let's look at the $18 price now. So the $18 price is going to be the square root of 2 times 20,000 times 40 divided by $3.60. And so we get our EOQ of 667. There's a 668, I guess. Here, hold on. 667, excuse me. Okay, so that is an EOQ. Now, can we buy 667 for $18? Well, the answer is yes, we can, because we can see that for that $18 price, we have to buy between $500 and $999. So this is a feasible EOQ. All right, so that's step 2. And then also, we don't need to evaluate the $20 price, because once we find a feasible EOQ, we stop going up. All right? So all we have are these 2 options to evaluate. Okay, so in terms of this use Q column, what we're going to do is, if it's feasible, we can use that EOQ. All right? So we're going to calculate now the holding cost with 667 is going to be 667 divided by 2 times the $3.60. So that's going to give us a holding cost of $1,200. All right. And then the ordering cost is going to be the demand of 20,000 divided by 667 times times the ordering rate, which was 40. So that's going to give us $1,200. Okay? All right, and this makes sense because we know at the EOQ, our ordering and our holding costs are equal. Now the purchase cost is going to be the price, which is $18 times the demand, which is 20,000. So the purchase cost is going to be $360,000. All right. And so our total is going to be the $360,000 plus the $2,400. So it's going to be, our total cost is going to be $362,400. And I'm going to put that right here. All right. So the total cost for the $18 price is the $1,200 in holding, the $1,200 in ordering, the $360,000 purchase cost gives us a $362,400 total cost. And again, we have to add the purchase price because price is no longer constant. Okay? All right, so now let's take a look at this where the EOQ is not feasible. So we can't use the 668. So what we're going to do is we're going to use the lowest quantity that we can buy at that price. And that's called the price break quantity. So we're going to use 1,000. We're going to compare this $17 price for the minimum that we can order at that price, which is 1,000. So we're going to use Q of 1,000 for the $17. And so if you calculate your EOQ is going, or I'm sorry, your holding cost is going to be the 1,000 over 2 times $3.40 So that's going to give you $1,700 here for the holding costs. And then if you look at the demand, 20,000 over 2, which is 1,000, times the 40, that gives you $800 for the ordering costs. All right, so we've got $2,500 here. And so if we look at the purchase cost, it's going to be 20,000 times $17, which is 340,000. So our purchase price is 340,000. Okay, so this is going to give us a total cost then of, hold on, I'm just 342,500. All right. So now you look here, we have a total cost of 362,400, and we have a total cost of 342,500. Well, the lowest total cost here is this one at the bottom. It's $17. So again, the answer to this is we're going to order 1,000 units at $17 each, and that's going to be the answer to the quantity discount kinds of example I gave you. All right, so I would recommend that you use this template. And again, if you want to use Excel to put these formulas in, you can. You don't have to use Excel, but again, it gives you a way to organize the information so that you could do the analysis. Okay, so here I've shown you an example of with the answer, and hopefully I got all these cells correct. Okay, so what we've just covered is how much to order. So basically, these two models, the basic EOQ model and the quantity discount model, they've told us how much to order. Now we want to know when to order. All right, and let's talk a little bit about when to order. So let me just draw here my sawtooth diagram. All right, so remember, this is how it looked. All right, so it would look kind of like a shark in the water. All right. Okay, so remember we said up here at the top is the Q, and we said that the slope was the rate of demand. Okay, so down here at the bottom, this is going to be time on the x-axis. All right, so the x-axis is time, and then the y-axis is quantity. All right. All right, so let's go back to our 20 gallons of milk example. All right, so let's say we use 20 gallons a week, or let's say we do 2 gallons a day. The lead time is going to be defined as the time that elapses from placing the order and receiving the order. Okay, so lead time, LT, is interval of time to place and receive order. All right, so this interval of time right here, this would be the lead time that I've just drawn here. This is the lead time right here. Okay, LT. Okay, so what we're going to do here is we're going to define a quantity that will trigger a reorder. So let's say that again we use 2 gallons per day, and we initially ordered our 20 gallons. So here we go. We kind of come up here. So here's our 20 gallons up here. Sorry, here 20 gallons. We order in 20 gallons, and we use 2 gallons per day. Let's say that our lead time, it takes us 1 day to go to the store and buy 20 gallons of milk. All right, so if the lead time is 1 day, then how much gallons of milk do we have need to be on hand that's going to trigger a reorder? And that's what the reorder point is, okay? So the reorder point is, again, going to be equal to it's a quantity, even though it's a time, okay? It kind of triggers us to make sure that we don't run out. So the reorder point is going to be equal to the demand times the lead time. And so in this particular case, the reorder point will equal 2 gallons per day times, and I said 1 day is the lead time, so it's going to be 2 gallons, okay? So if I buy my 20 gallons of milk, and so after the first day it's going to be 18, after the next day it's going to be 16, so I'm monitoring what I have on hand. And when I get down to 2 gallons of milk, that is my reorder point. So that means, I got to go and buy 20 more gallons, because if I don't, I'm going to run out. So that's what the reorder point is. So what affects it? Rate of demand. So you can see the higher the demand rate is, the greater your reorder point will be. The same with the length of the lead time. The greater the length of your lead time, the bigger your reorder point is going to be. If you have demand and or lead time variation, you're going to have a higher reorder point to compensate for that. And then we'll also talk a little bit about stock out risk. So if you want to have a really high service level or a very low stock out risk, then you're going to have a bigger reorder point because, again, you're going to have to carry safety stock. All right. All right, so let me do one more thing here. It says the reorder point is expected demand during lead time plus safety stock. So again, if I were to draw my sawtooth diagram here, now here's my rated, let's say my rated demand is unknown, okay? So it looks something like this. All right. So what we have here, and so let's say that this is our lead time right here, okay? Okay. So the expected demand during lead time is just this interval of time right here. That's the only time we're exposed to a risk of stock out is when we're waiting for that next reorder to come in. And so the reorder point is going to be what's happening during just that specific period, plus then this part right here is safety stock. It's what you have in case your demand exceeds supply, okay? So this is what we're going to use. Now, when in the EOQ model where I had demand was known and constant, so with EOQ, then ROP is going to be D times LT plus 0. In that case, safety stock is 0 because you wouldn't need safety stock. Your demand is known and constant. Your lead time is known and constant. There's no way you're going to run out. You know everything. So in that case, safety stock is 0. But that situation is very rare. Usually there are lead time and demand variations that we have to compensate for. So we're going to look at some other models that allow for the more realistic demand and lead time variation. Okay, so before we get into that, think of, again, this demand during lead time as being a normal distribution curve. All right, and so the demand during lead time, the mean of this, what's happening during the lead time is kind of this is the mean right here. Okay, this is demand during lead time, the mean, the average. What happens on an average period? All right, now, if we look at the area under the curve, if we just carry what we expect on the average, then we're only going to be able to offer a 50% service level. And the service level is going to be the area of this curve. All right. So if we want a 50% service level, we carry no safety stock. It's just that simple. We're only going to be able to meet average demand. Now, usually that's unsatisfactory to many companies. They want to offer, for instance, like a 95% service level, which means 95% of the time they're going to be able to serve an order, an unexpected order, okay? So so what they'll do is they'll have a reorder point that is higher, okay, than the expected level. And so then the area under this curve now is much higher than 50%. But we've added on some additional inventory here that has come out to the right of this distribution curve. Now, this reorder point is a certain number of standard deviations away from the mean, and we're going to use that to represent that reorder point with a z-value, okay, from statistics. Now, this part of the curve here, so remember I was saying if you have like a 95% service level, well, that means 5% of the time you're going to stock out. Well, the area to the right of the reorder point is the risk of stock out, all right? So again, if in this case it would have been 5% would be the area of the risk of stock out there. And then the 95% would be my service level. And I could find that. How far that reorder point is going to be to the right is going to be a function, again, of that z-value, which is a function of the area under the curve that we want to cover. All right? Okay, so when you're solving reorder point problems that have demand and or lead time variation, the first thing you want to do is you want to determine if demand, if lead time, or if both of them are variable, all right? Then you can determine a service level. Or they'll either give you a service level or they'll give you a stock out risk. Once you have either one of those, you can find the z-value. And then you can find the appropriate formula to use and then solve for reorder point. And if they ask you about safety stock, well, safety stock is just the amount after the plus sign in a reorder point equation, okay? All right, so let's go and do an example. This is problem number 32. All right, it says, given that your average demand is 1,000 per day, and your standard deviation of demand, that's sigma d, is 100 per day. And if lead time is 2 days, and if your service level is 98%. Okay, so if you have a service level of 98%, what you're going to do is you're going to go to the z table, and you're going to find the z value that gives you a 0.98 area. Or you can just use Excel, and you can find that that value is, the z value is 2.05. All right, so if we are 2.05 standard deviations above the mean, we will cover 98% of the area under that curve. All right, now if you notice, another thing you notice is you're given an average demand and a standard deviation demand. This is a variable demand, constant lead time problem. So whenever you're given standard deviation, either of lead time or demand, you know that that's variable because standard deviations come with distributions, and distributions mean that you're not dealing with one number but a distribution of numbers. So the variable demand constant lead time formula is basically, I'll just type it right here, right above here. So this is our reorder point equals D times lead time plus Z times sigma D times square root of lead time. Okay, so that is the formula for a variable demand constant lead time problem. So you just put that in, and you can find out that your reorder point is 2,290. The safety stock is anything after the plus, which would be 290. Okay, so again, this is, you have to find out what you're given, find out your Z value from the area, and then figure out what type of formula that what they're giving you falls with, okay? That's the easiest way to do these problems. Okay, another example. They give you that the average demand during lead time is 50. They give you that the standard deviation of demand during lead time is 5. And they give you a service level of 97%. So again, we can use the equal norms inverse, or we can just go to the Z table. We can find out that the Z value that covers 97% of the area is 1.88. Then in this particular formula, when we have the distribution of demand during lead time, the safety stock is going to be Z times sigma DLG, which is going to be 9.4. So then the reorder point is the demand during lead time, which is 50, plus the safety stock gives us a reorder point of 59.4. So the last example, well, I didn't do an example, but again, if you look in the book, they give you reorder point formulas for variable demand, constant lead time, constant demand, variable lead time, variable demand, and variable lead time. And then also when you're given the distribution of demand during lead time. That's equation 12-13. So the reorder point part does have a lot of formulas, but again, you just need to really read the problem, see what you're given to be able to select the appropriate formula to solve for either the safety stock or the reorder point. Okay, so just as a friendly reminder, so there's a couple things due this week. Today is Monday, so your first exam is going to be due Wednesday. I believe I set the due date on that. And then also your Chapter 12 homework will be due this Sunday at midnight Central Time, okay? If you do have any questions, feel free to let me know via the discussion board or email me directly. And hopefully you have a good week. So I will talk to you all next week. And again, if you need anything, just send me a quick email. All right? Take care. Bye-bye.